3 elections, 3 landslides, 3 different winners. How can one set of voters produce all 3? Exactly 99 voters split into 3 equal groups of 33. The first group ranks A above B above C. The second prefers B, then C, then A. And the third chooses C, then A, then B. The first and third groups both prefer A to B, so A wins 66 to 33. The first 2 groups both prefer B to C, so B wins by the same landslide. The last 2 groups both prefer C to A, so C also wins 66 to 33. Every contest is decisive, so who wins the election? Choose A versus B first. A advances, but C beats A and takes the crown. Start with B versus C. B advances, but A beats B and takes the crown. Start with C versus A. C advances, but B beats C and takes the crown. Same voters, same rankings, only the order changed. This loop is called a Condorcet cycle. When preferences cycle, whoever controls the agenda can control the winner. That is the first crack in a perfectly fair voting system. But perhaps majority voting is the problem. Could a cleverer rule escape every crack without handing control to the agenda? Feed the machine every voter's ranking that honest voters might report, with no forbidden ordering of A, B, and C. It must return one complete, consistent social ranking, not a loop and not a shrug, because collective choices cannot contradict themselves. If every voter puts A above B, the social ranking must also put A above B after that unanimous change. When comparing A with B, only each voter's A versus B judgment may matter, whether C rises, falls, or disappears. And no single voter may have their entire ranking copied as society's answer against all others every time. Unrestricted input, unanimity, independence, no dictator. Each lock sounds reasonable alone. Pause and choose which lock you would sacrifice to keep the machine running. Arrow's theorem says that with at least 3 choices, no rule can keep all 4 while returning a complete, consistent ranking. To see why, forget scores and follow one group through a pairwise test because the proof tracks power rather than vote totals. Let everyone inside the group prefer A to B, while every outsider prefers B to A on that one question. If society still ranks A above B, call that group decisive for this comparison, even when outsiders unanimously oppose it. At least one decisive group always exists, the whole electorate, because unanimity already guarantees it for every candidate pair. Now comes the relay trick. Once the other locks are kept, decisive power cannot remain trapped in one named pair. Insert C between A and B across several allowed ranking profiles, then move C without changing anyone's A versus B judgment. Independence freezes society's A versus B answer whenever those pairwise judgments stay fixed, as if C were never there, and a consistent social ranking forces the comparisons through C to line up, carrying power from one locked comparison to another. Repeat that relay with renamed candidates, and one decisive pair expands into every pair, a move usually called field expansion. Because the electorate is finite, choose a decisive coalition containing as few voters as possible among all such groups. Suppose this smallest block still contains more than one voter, perhaps a whole crowd. Split it into 2 non-empty pieces, left and right, keeping both pieces inside the original boundary while everyone else stays outside. Give the left group X above Y above Z, and the right group Y above Z above X, so both orders remain directly countable. Every outsider ranks Z above X above Y, opposing the original coalition wherever it matters, and creating the final polarized profile. Both halves rank Y above Z, so the original decisive coalition forces society to rank Y above Z, even while every outsider reverses that pair. Now society must rank either X above Z or Z above X. Pause. Which branch saves minimality before either answer is revealed? If society chooses X above Z, the left subgroup has defeated everyone who preferred Z above X in this exact polarized profile. That makes the left subgroup decisive for one pair, and field expansion ensures its advantage is no one-off accident. If society chooses Z above X, transitivity combines Y above Z with Z above X, forcing Y above X with no possible cycle. But only the right subgroup preferred Y above X against everyone else, so after field expansion, the right becomes decisive. Either branch creates a smaller decisive coalition, contradicting our claimed minimum, so neither branch can preserve a larger smallest group. So the smallest decisive coalition cannot contain 2 people. Finite groups cannot shrink forever, and the process stops at exactly 1. The relay now spreads that single voter's decisive power from one pair to every pair. Whatever the other voters report, society must copy that person's ranking whenever choices are compared. That voter is the mathematical dictator. Not a ruler, but one ranking that becomes society's ranking. Return to the fairness machine, and the mystery resolves. Keeping the other promises breaks no dictator. If dictatorship is forbidden, then at least one other promise must bend or break. Runoffs and ranked choice methods let eliminated candidates affect later comparisons, so independence can fail. Approval and score voting ask for more than rankings, leaving Arrow's original input model. Restrict voters to single-peak preferences, and majority comparisons can line up without the opening cycle. Arrow did not prove democracy impossible or that every voting rule is equally bad. He proved that these attractive promises cannot all coexist inside one unrestricted ranking machine. Every voting system spends fairness somewhere. Ask which promise it trades away and whether that trade fits the decision. Strategic misreporting opens an entirely new impossibility behind the next door.